Okay, I'll start sharing my screen. Since I'm out of my office, if there's a point where you cannot hear me fine, let me know. Okay, so to try to fix that. So we're going to be talking about something called arch and gauge models, and that's as I was saying, we're starting to use presentation 14. The name arch because they are essentially conditional heteroscedastic models. And we have so far made the assumption that the variance is constant on time, right? So as long as time goes through, the variance remains constant. Well, so that's not always the case. So that's why when that happens, we use these models which are called arch because they are autoregressive conditional heteroscedastic models, and gauge models, which are generalizations of these arch models, which are generalized autoregressive conditional heteroscedastic models. You'll see why why the name is that as soon as we start talking about what they try to model. Okay, these are the two references. They were developed. The first model and arch model was developed by Engel, and then the generalization was made by Bolster, and many years ago. So we many problems in financial and economic time series, such as option pricing, for example, have a motivated study of this type of models. Because in those types of financial series, what's more important is to study the volatility or variability. Okay, when we talk about volatility, essentially we're talking about variability over time series. These models, when you have a series like this is the Dow Jones returns. That's one of the charts that we saw at the beginning of the class. These represent the percent change in Dow Jones returns, daily returns, from April 20th, 2006 through April 20th, 2016. So as you can see, the series is fluctuating around the mean value, a constant value. And what is relevant here, so if you want just to try to model this series in forecast, the forecast will be a straight line. When we have this type of data, the interest is more on understanding volatility, which is variability, rather than forecasting the mean value of the series or the expected value of the series. If in this type of series, you will see that periods of high volatility are followed by periods of high volatility. They group together. So this group of points here, which have high volatility, are grouped together. These also are grouped together. In points where we have low volatility, that is low variability, they are also grouped together. That's the main characteristic of this type of models. So I mean, usually looks stable, but the volatility is what's important and what's relevant in this type of models. The way we are going to address and define these arch models, the first starting with the arch model, is we're going to denote by R sub t the return rate of a time series. That is, R sub t is going to be the difference between the time series at time t minus the time series at time t minus 1 divided by the value of that series at time t minus 1. So it's a return rate of that time series. How that rate of return is behaving. We're going to be calling that R sub t, the rate of return. Now, if this is how we're defining the return, Then ZT from here, we can get that it's 1 plus the return times ZT minus 1, which is the observation at time t minus 1. Now we're going to be dealing with series that are going to be maybe hourly in some cases or daily. So we expect the returns to be a small percentage of the previous observation. So if we're sitting at CT, and we expect that CT minus 1 divided by the observation at time t minus 1, that which is the return will represent a small percentage of RT minus 1. So we don't expect huge changes from one period to the next, because we're dealing with this. Usually we're dealing with small periods of time. Sorry. Okay. If this is the case, if these rates of return are small percentages, then the difference in the log of the CT, the time series, is going to be approximately equal to the return. Okay, because this ZT, if this is small, then this expression here will be very close to the log of the difference of the logs, right? This is going to be very small, so we expect this to be very close to the difference of the logs of ZT minus the log of CT minus 1. So this will be approximately equal to the return, so that's the log of CT minus the log of ZT minus 1. That's going to be approximately equal to the return. And we will actually be referring to the differences of those logs as the returns also, because they're very close in general. Okay. So both the first difference of the log of the series and ZT minus CT minus 1 divided by CT minus 1 we'll be calling those two figures, which are very close, the return. And we'll be denoting those returns by R sub t, okay? R sub index t. Now, typically, in financial time series, the returns R sub t do not have constant conditional variance, okay? So different from what we have seen so far, where we have assumed that our series has constant variance, the series of returns will not have constant variance. The variance of the returns conditional on the past will be different, will be changing. And as we saw in the previous chart, high volatility periods will be close together and followed by low volatility periods, and the low volatility periods will also be clustered together. Okay? We'll see groups of how the variability is changing, and we'll have high volatility next to high volatility and low volatility next to low volatility, like the example we saw in the previous chart. Okay, are there any questions so far? Okay. Now, the simplest model, let's start as we have done in the past. We will start with the simplest model, which is the arch of order 1 model. The arch 1 model is going to model the returns as follows. The model will consist of these two equations, essentially. One, the first equation tells us that the return at time t is equal to the standard deviation at time t times some epsilon at time t, okay? So as you can see, the returns will depend on the standard deviation at time t. That's one of the one of the important things to notice here. And the variance, which is the sigma t squared, will be expressed as a function of RT minus 1. So if you look at this expression here, this is essentially like an AR1 model for the returns, right? Because I have that sigma t squared, the variance depends on a constant, plus alpha 1, the return at time t minus 1 squared. Okay, so it's alpha naught, which is a constant. We're going to estimate that constant, plus some other constant, alpha 1, times the square of the return at time t minus 1. And the assumption is that the epsilons, these errors here, are independent, identically distributed as normal with a standard deviation 1. That's the usual assumption for this type of models. This is called an Arch-1 model, and it involves both equations. The equation for the return, which is, it just says that the return is a multiple, a random multiple, let's call it like that, a random multiple of the standard deviation. And the second equation, which is telling us that the variance is a function of the return squared from the previous period. So it's the square of the return at time t minus 1. The two models comprehend what represent the AR1 model. So these two together, these two equations go together. Now, here we have a clear restriction. We know that the variance is always positive. So we're going to restrict the models so that alpha 0 and alpha 1 are both greater than or equal to 0. Why do we do that? To avoid the risk of having an alpha 0, for example, which is negative, and can make this thing negative, which wouldn't make sense. So we have a restriction on the coefficients for this model for the variance. And the conditional distribution of RT given RT minus 1. So if I look at the distribution of RT conditional on the return one period before, it's going to be a normal distribution with mean 0 and variance equal to exactly this equation here. Okay, that's the Arch-1 model, which involves these two equations plus this restriction, and the conditional distribution of RT given RT minus 1 is going to be normal, and the variance will be alpha 0 plus alpha 1 RT minus 1 squared. Now, we can write this model as a non-Gaussian AR1 model, right? If we square the returns, if you take this equation and square it, you get RT squared equal to sigma t squared times epsilon t squared, right? Now, this epsilon, we call it a non-Gaussian because the epsilon t squared do not have a Gaussian distribution. Okay, the ATs have a normal distribution, but these do not have a normal distribution. The AT squared do not have a normal distribution. And the second equation we will express, we'll just put it in the different order. We'll put this on the left side, alpha 0 plus alpha 1, RT minus 1 squared equals sigma t squared. Now, with these two equations, if we subtract both equations, we get that RT squared. So we're going to subtract this equation from this equation. So let's say this is 1 and this is 2. So we take 1 minus 2 gives us that RT squared minus alpha 0 plus alpha 1 RT squared equals to this sigma t squared epsilon t squared minus sigma t squared. So that's just the difference of the two equations. And this equation here, we can write it as the square of the return at time t equals to alpha 0 plus alpha 1 RT minus 1 squared plus nu t. Now nu t is playing is taking the place of the random error, right? But nu t is equal to sigma t squared times epsilon t squared minus 1. Epsilon t squared, if epsilon t is normal 0, 1, remember that epsilon t is normal 0, 1. So from here we know that epsilon t squared is a high square distribution with 1 degree of freedom. But see, if we take et squared and we subtract 1, we have an uncentered high square distribution, a shifted high square distribution shifted by 1 unit. Okay. So nu t is no longer a normal distribution. It's a variable, random variable, which has an uncentered high square distribution. That's why we call this thing a non-Gaussian AR1 model. But if you look at this equation, this looks like an AR1 model for RT squared, right? Because I can write this equation here. I can write it as 1 minus b RT squared equal nu t, which is, and this is a non-Gaussian, AR1 model. That's the model for the return, the square of the returns. Okay, so the square of the returns will have an autoregressive of order 1 model, but it's non-Gaussian because the errors, the nu t's, which represent the random error in this case, are not Gaussian, are non-centered or shifted high square distribution. Now, if we define capital R sub S as the returns at time S, S minus 1, S minus 2, S minus 3, and so on, then the expected value of the return at time t, given all the returns up to time t minus 1, which is what this thing is saying, is the expected value of RT, which is the return at time t, given that we know all the returns from RT minus 1, RT minus 2, RT minus 3. Okay, so that remember this is RT minus 1, RT minus 2, and so on. So we have all the past returns. The expected value of those returns is going to be 0. And this is the reason why the process RT, which we can also look at as stochastic process, is what's called a martingale difference. I don't know if you recall the term. When you took stochastic processes, what a martingale difference is, this is the characteristic that makes this a martingale difference. It makes the returns a martingale difference. And since they are martingale difference, they are a uncorrelated sequence. So these returns are not correlated. The returns are not correlated. It's an uncorrelated sequence because they are martingale sequence. In fact, the errors, the nu sub t's, which have this non-centered high square distribution, are also a martingale difference and therefore are not correlated. So the nu sub t's, which are these errors, are not correlated. They do not have normal distribution, but they are not correlated. And given that we have expressed RT squared as this AR1 model, a non-Gaussian AR1 model, the expected value of RT squared and the variance must be constant. Okay, that is, they must not depend on t, on the time, because they are an AR1. They hold an AR1 relationship. And we have made the constraints. Remember that we made the restriction here. We made the assumption that alpha 1 is greater than or equal to 0. But we will also have another assumption that's clear, because for this thing to have an AR1 model, which essentially we're meaning a stationary AR1 model, alpha 1 is also will have to be less than 1 in absolute value. In actually less than 1, because it's going to be positive. Okay, are we doing okay so far?
Yes.
Okay. Now, in fact, the expected value of RT squared is going to be the variance of RT, because the mean of RT squared is 0. So the expected value of RT squared is the variance. And that's equal to alpha null divided by 1 minus alpha 1. That's going to be the variance. So it's a constant variance. It doesn't depend on t. And the variance of the square of RT, the variance of the square of RT is going to be equal to the 3 times alpha null squared. We can do the algebra, but it's really not necessary to do the algebra here. The variance of RT squared will be the expected value of RT squared minus, okay, remember that variance is going to be equal to what? This is going to be equal to the variance of RT, sorry, of RT squared is the expected value of what? Of RT squared minus its expected value, and the expected value of RT squared is alpha 0 divided by 1 minus alpha 1. All this thing is squared, right? That's the variance of RT squared. And if you do the algebra, you'll see that that's equal to that expression on the top, which is 3 times alpha 0. That's just algebra, okay? 3 times alpha 0 squared times 1 minus alpha 1 squared divided by 1 minus alpha 1 squared times 1 minus 3 alpha 1 squared minus alpha null divided by 1 minus alpha 1. That's the variance of RT squared, which again does not depend on t. The important thing here is that it doesn't depend on t. Okay. Now, this expression here will exist, this ratio and the difference here will only exist if alpha 1 is between 0 and 1 sub over square root of 3. Okay, we need that alpha 1 be between 0 and 1 divided by square root of 3. Why do we need that restriction? That restriction comes up, essentially, this restriction comes from here, right? We need this thing to be finite, so we need essentially to have the alpha 1 squared be less than 1 over the square root of 3. So when we square it, we get something that's less than 1. Okay? Because we need the variance to be positive. Okay. Now, we can show, again, it just remember the definition of kurtosis, and it can be shown that the kurtosis of the marginal distribution of the returns is greater than or equal to 3. What that means is that the distribution of returns will have heavier tails than the normal distribution, because the kurtosis is greater than the kurtosis for the normal distribution. So the tails will be heavy. Now, if alpha 1 is between 0 and 1, RT is quite nice. And if 3 times alpha 1 less than 1, that is RT squared satisfies the relationship of just on the previous slide, then RT squared follows an AR1 process, which is the one we defined already. And how do we estimate alpha 0 and alpha 1? We estimate alpha 0 and alpha 1 by maximum likelihood, but it's conditional maximum likelihood because it's conditional on the previous returns, on the returns up to time t. So that's a method we use to get the estimates of alpha 0 and alpha 1. It's maximum likelihood. We can also combine a regression model or an ARMA model for the mean. So that is, we have we can model the mean of the series with a regression model or with an ARMA model, and then model the errors with an arch model, because the errors will not be normal, so we'll need to use an arch model to model the errors. That will become clear when we start doing some exercises to try to model this volatility in this type of time series, financial and economic time series. For example, if we have, suppose that for the mean, I have a regression model of this form. So we have a regression model that says that the series XC is vector of constants, which are going to be estimated, times ZT plus YT. And YT is this is playing the role of the error, right? And I have a regression model. Remember, in the regression model, remember the typical regression model is Y equal to beta prime times X, which are my independent variables plus epsilon, right? That's the traditional regression model. Now, we don't have in that model, the epsilons, remember, under the assumption, when we studied the regression analysis, we usually make the assumption that the epsilons are normal. Now, what we're doing that is we're not using that model. We're doing a regression model that involves the ZTs, which is the original series, plus YT, which is representing the error. But YT is now sigma t times epsilon t. So my error is not normal. And then my second equation for the arch model is sigma t squared equal alpha naught plus alpha 1 YT minus 1 squared with epsilon IID normal 0, 1. The epsilons are normal 0, 1. So essentially what we say here in this statement is we're modeling the ZT, our series, as a regression that involves the observations ZT plus a random error, which is not normal because it's equal to sigma 1 epsilon t, and sigma t squared is equal to this expression here. So this is the regression model, this is the arch model, and this is the regression model. Regression model for the mean, for the behavior of the series, and an arch model for the errors. That's essentially what we're doing there. Now, instead of a regression model, we could be fitting an ARMA model, for example, for the errors, okay, for the mean, and an arch one model for the errors. For example, maybe the model for the mean of the series is xt equals phi naught plus phi 1 xt minus 1. So it's an AR1 model instead of a regression model. It's an AR1 model for xt. And I add the error yt, and then I model the error yt with an arch model, which would be this one here over here, with the yt having this represented by these two equations. Okay, so this is as if you copy these two equations and put them down here, right? That will be the complete model. An ARMA model for the mean, and an arch model for the errors. Now, of course, what we're going to be trying to do, we're going to try to do the estimation of the parameters, both for the regression or the or the ARMA model, together with the parameters for the ARCH model simultaneously. So we will maximize, we will estimate the parameters simultaneously. That is, we don't estimate the parameters for the ARMA model first and then do the estimation for the ARCH model, but we do the estimation simultaneously. Let me try to erase these things. I can erase them from here. Go back here to erase this. Annotate your drawings. Okay. So now the arch and what's an arch? An arch of order P, an arch P model is going to be something very similar to what we saw, but instead of involving only one return squared, only the prior return squared, will it involve the previous P squared of returns. That's why we call it an arch P of order P, because we'll have the same equation for the return. That's exactly the same thing. But then sigma t squared is going to be a function of RT minus 1 squared, RT minus 2 squared, up to RT minus P squared. So that's going to be an arch P model. So we'll have the sigma squared, the square of the variance. The variance at time t will depend on the square of the returns at time t minus 1, t minus 2, up to t minus p. That's why it's called an autoregressive conditional heteroscedastic model. Okay, autoregressive conditional heteroscedastic model. The Garch model, which is a generalization of the Arch model, what it does, it adds some other coefficients that could play a role for the previous returns. So, for example, the Garch generalized Arch model, for there's 1, 1, would involve the square of the return at time t minus 1 and the square of a return at time t minus 1, but multiplied by different numbers. So this model gives more flexibility because we have two different parameters here that affect the returns at time t minus 1. So there'll be a Garch 1, 1. That'll be a 1, 1. And of course, that can be generalized to a Garch P comma Q, and how do you imagine the Garch P comma Q is going to look? Before we go in an example here, if I had a Garch P comma Q, what I would have is something like, if I have a Garch P comma Q, then I would have sigma t squared equal alpha naught plus alpha 1 RT minus 1 squared plus alpha p RT minus p squared, then plus beta 1 RT minus 1 squared plus beta t minus p, this t minus p, and this will be plus beta q times r t minus q squared. Okay, that will be a generalization for the Garch model of orders P and Q. Now, for a Garch 1, 1, for a Garch 1, 1, alpha 1 plus beta 1 must be less than 1. Both have to be less than 1. And the model also, as in the Arch 1 model, it admits a non-Gaussian ARMA model of orders 1,1 for the square root of returns. Okay, so it's equivalent of the arch model, but we are adding a second set of parameters for the returns, for the square root of returns also. So to provide more flexibility in modeling. So the RT squared is going to be equal to alpha, for a gauge 1, 1. It's going to be equal to alpha 0 plus alpha 1 plus beta 1 RT minus 1 squared plus nu t minus beta 1 t minus 1 sigma square t minus 1 square. And nu t is going to be, just as before, is going to be sigma square time t times epsilon t square, which is a shifted high square distribution with 1 degree of freedom, because the epsilons have a normal distribution with mean 0 and standard deviation 1. Okay, so that's going to be the model in a gauge 1, 1. And for a gauge PQ, that will be the expression, correct, which is the same that I wrote earlier, just expressed with sums here, which is going to be alpha null plus the sum up to P of the alpha, the alpha parameters times the returns, the square root of returns, and a sum of Q parameters, B beta, times the square root of the returns. And the epsilons are IID, normal 0, 1. It's exactly the same thing. It's just a generalization of the gauge 1, 1 model. Okay? Now, in practice, it'll be very strange that you find very high order gauge models. That's going to be very rare in practice. We will usually end up with gauge, simple gauge models, 1, 1, at most 1, 2, or 2, 1, or something like that. But we very seldom get to model something with more than an order 1 or 2 gauge. Okay? But you see, that's why we're calling the names here P, order Q, because of the similarity with an ARMA PQ model. Are we doing okay so far?
Yes, teacher.
Yes.
Okay, good. Now, how do we build gauge models? To model conditional heteroscedasticity is equivalent to complementing a dynamic equation that represents the evolution of the conditional variance as a time series model. Essentially what we're doing is complementing a dynamic equation to represent that will represent how the conditional variance changes over time, and that we do that with a time series model, essentially. What are the steps in building a gauge model? So I'll be talking mostly about gauge models, although because arch without the G is just a simple, particular case of a gauge model. Okay. Now the first thing we do is we analyze the series and specify an equation for the mean. Okay. This could be done either by a simple regression model, or we may need an ARMA model to model the mean. So that's the first thing we do. We have our time series that represents the returns for the Dow Jones, for example. Then we fit an ARMA model for the series. Once we do that, I mean, either an ARMA model or regression model. Actually, a regression model could be viewed as a particular case of an ARMA model. And then once we have that model, based on the residuals, we're going to define how to fit a gauge model. So the first thing we do is we model the mean, that is, we model the serial dependence of the series. Then we use the residuals of that model to test if there are arch effects. That is, if there are conditional heteroscedastic effects. If the arch effects are statistically significant, we specify a model for volatility. We'll see how we determine if there are arch effects, okay? But first we use the residuals, determine if there are arch effects. If the arch effects are statistically significant, then we specify a model for volatility, okay? And we jointly estimate the equations for the mean and the volatility. So there's essentially two stages. I model the series, analyze the residuals, determine if there is an arch effect, that is, if I have a behavior that's attributable to conditional heteroscedastic behavior, and if the arch effects are statistically significant, then I specify a model for the volatility, and then I do in a third step, I put everything together to do a joint estimation of the model for the serial dependence of the series and the arch model. So we estimate simultaneously the ARMA models, the ARMA model parameters and the arch model parameters. And then, of course, as usual, we test the goodness of fit of the model. We check if the model is satisfying the conditions for that, the residuals and all that, for that final model, if they behave the way they should and stuff like that. Essentially, that's what we do. Okay. Now, how do we test for arch effects? Let's define A sub t equal to RT, which is the series of returns, minus its mean, minus the mean at time t, okay? So these are the residuals from the equation for the mean. And this equation could be an ARMA model or could be a simple regression model. Okay? So we calculate the ATs, which are the residuals for the model that we use to model serial dependence of the returns, minus its mean. And then we're going to use the square of these errors. These are the errors. These are the residuals once we fit the model for the mean. Okay. Once we fit the ARMA model for the mean or the regression model for the mean, the ATs represent the residuals from that model. And then we use the square of these residuals to do the test for conditional heteroscedasticity. That is, we do the test for arch effects using the square of the residuals of the model that we use for the mean. Here there are two tests that can be used. Okay. One is the Young box statistic. We have used that before. We know that in this Young box statistic is that the first n periods of the squared residuals of the ACF is 0. So we calculate the squared residuals and calculate then the Young box statistic for the square of the residuals, and it check if these p-values are small. Remember when we were modeling the time series, not modeling conditional heteroscedasticity, we wanted the p-values to be large, right? Because that meant that we did not have autocorrelation in the residuals. Here, the proof for arch effects is if we have autocorrelation in the AT squares, in the squares of the residuals. So small p-values for the first 3 lags, 4 lags, 5 lags, and so on will indicate the presence of an arch effect. The second test is a test that's based on Lagrange multipliers. This test is equivalent to an F-test of a null hypothesis that alpha I, all the coefficients, are 0 in a regression model. That's equivalent of the F-test in regression. So we're testing the hypothesis that all the coefficients are 0 against the alternative that at least one of them is different from 0. And the way we do this test is, again, based on the square of the residuals, which are these AT squares. We model the AT squares as a regression model. Alpha 0 plus alpha 1, AT minus 1, plus alpha n, AT minus m squared. Okay, t equals from n plus 1 up to n, up to capital N. And then we compute the F-test just as we do it in regression analysis. We compute the sum of squares of the residuals for the null model, which is we usually denote by R0, SS R0. That will be the model where we only subtract the mean. Okay, that's the residuals when we subtract the mean. And then we compute also the sum of squares due to regression, which is essentially the sum of the errors squared of the regression model. And then we compute the F ratio as the ratio of the sum of squares of the null model minus sum of squares of the regression model divided by the number of degrees of freedom, which is m, the number of parameters, and that divided by the sum of squares due to regression divided by the degrees of freedom of the sum of squares due to regression, which is n minus 2m. M is the number is the order of model, times 1. And that is approximately a chi-square under H0. So that statistic has approximately a high square distribution with n degrees of freedom under H0. The test we'll be using here, because that the easiest one essentially to be doing, is this one. This is the test that we'll be using to check if we have arch effects or not. Okay, we'll be using the Box-Young statistic to check if there are arch effects or not. Now let's work an example with the gross national product in the US from the first quarter of 1947 through the third quarter of 2002. I'm going to switch to R. Okay, switch to R, and let me go now and show you when to look at the script ST14 gauge modeling. You have it right space, and download this script. Okay, download this script ST14 gauge modeling. Once you download the script, run all the package installations, and up to when you really look at the structure of GMP series, which comes with the I believe it comes with the widget forecast package, I believe. So you load all the packages and run up to line 47. Okay, and let me know when you're ready. So we're taking the log, and again, as I was saying, remember we said that the difference of the logs, we'll be calling that the return at time t. Okay, so I'm going to do the plot of the log, and we'll do the autocorrelation function of the log. It's clear that we need to make a difference, so we'll take the ACF. This is the plot of the first difference, and this is the AC. Okay, so this chart, we can see here that the first lag in the partial autocorrelation function is significant, less than 0.5, and we have here, we have decay. Okay, that seems to be like a sine wave here, right? So this, the first model that we can think of is an autoregressive of order 1 model. And that's what we're gonna do first. We're gonna fit an autoregressive of order 1. So we'll be working with the returns. That's the logs. The difference of the returns will be the difference of the logs, right? So I'm going to be calling, actually I could change the name here, and I could use this thing. Let me make the change. I'm going to call this, to make it, to relate to the nodes, I'm going to make RT is going to be the difference of the log of GMP, right? So that's already the difference. So I'm going to model the RTs. RT. I'm going to model RT with an AR1 model, because we saw that the right model for the difference is an AR1 model. Okay. We'll model the GMP1, which I could call it, I could change also here to call it a model for the return time t, right? I could do that also to make it sure, to make it clear that we're modeling the returns. Okay. And let's look at, I will not make that change, but remind me that I made the change for RT, so that I refer to RT again next time from here on. So we can see that the AR1 model, the AR1 parameter is not significant, right? I have a p, I'm sorry, 0. I was looking at this column and the p-value is 0. The AR1 parameter is significant. So that was the right model. The graph here looks reasonable. And since when we're modeling arch effects, it's a two-stage process. The first model doesn't have to be perfect, but we need to make sure that we, at least this young box statistic behaves the way it should. Okay, we need to have larger p-values here. Now, this is exactly the same thing as modeling the log GMP with one difference, right? It's exactly the same thing. So I'm modeling the first difference of the log. So I'm going to get exactly the same thing. Now, let's analyze the square of the residuals. So remember that when I look at this, the model GMP2, I don't know how I called it here. Let's see, let me see here the structure of model GMP1. Remember that in the structure of this model, I do have the fit, and within the fit, I have the residuals. So I'm going to use the residuals now. So I'm going to use the residuals squared. So I'm going to change a little bit the notation here to make it more closer to the notation in the nodes. So I'm going to use AT squared is going to be equal to the mod GMP1. I'm going to use the first model. I did not fit the second model because it's the same model. If you want to verify that, you can run these two lines, but it's exactly the same model. The same, you'll get the same value for the parameter and so on. GMP1, residuals, fit, residuals, and I'm gonna square this thing, right? I'm gonna square the residuals. why not do it here? I'm doing it here. Let's see. It's no, that's it. Square. So I'm going to call that 80 squared, right? And then I'm going to look at the autocorrelation function, sample and residual and partial autocorrelation function of the residuals squared. So I'm going to use ACF2 of 80 squared. Okay, that's the ACF of 80 squared. Now remember the test of for arch effect, we do that test using the Young box statistic. So I'm going to use the values from 80 squared to compute the p-values for the Box-Young test. Okay, so I'm just going to change the values here. It is z. Okay, this is just the function. We have seen this function here, and I'm going to do the Box-Young test of 80 squares. Right, sorry about that. Of 80. I put the caps lock. 80 squared. 36 lakhs. I'm going to run that. And since my p-values, particularly we're interested in the first few lakhs, because that's what matters for an arch effect. Since the first few lakhs, I have p-values that are smaller than 0.05, they're very small, then I can conclude that there is an arch effect. Okay, so given the test, we know that there is an arch effect. Now we're going to use another arch to adjust both models together. We need to adjust the AR1 for the returns plus the arch1 for the residuals. Okay, so I'm going to use the function Garch feed from package Garch, I think is the name of the package. It's right here. It's 068 or model metrics. No, yeah, it is here. It's a fgarch package. So I'm going to use that function. And to fit the model for the series together with the model for the residuals for the arch effect. So I'm going to use, remember, we identified an ARMA 10 for the returns, and for the model for the residuals, it's hard to distinguish just based on the ACF and the PACF of the first. If we look at this thing, this could give us a hint of which model to use, but it's very difficult to see it from here. So we normally start with simple models and then increase the complexity if required. So I'm going to start with an arch1 plus an AR1. So I'm going to do the ARMA 10 for the series plus a Garch 10, and here I'm modeling the returns. Log GMP, the difference of the log of GMP, remember, are the returns, right? Are the returns. I'm missing one. I have one parenthesis. I don't need there. So I do the modeling. This is what this thing is doing, is fitting by maximum likelihood, and that's the model. Okay, that's the parameter, that's the mean. This is the autoregressive of order 1 parameter. This is the omega parameter. Well, the omega here is equivalent to the alpha nov. Okay, that's the alpha. This is alpha 0 essentially. This one here will be alpha 0 and alpha 1. Okay, because I fitted that an H1 model. Okay, so that's no, these are not the parameters. Let me get the summary here. These are not the parameters. That's the Hessian matrix. Let's look at the summary. And now it will have the p-values for the parameters. So as you can see, I have several tests here. We usually will be basing our analysis on the combination of these tests. But since we are using the jump box test to determine if there's an arch effect, that we will giving more weight to the box-jump test statistic. So, and we will normally be focusing on the first few lags. So this is the jump box test for the first 10 lags of the residuals of the complete model. Okay, that's for the residuals of the complete model. And that's a p-value that's large. So we feel comfortable about this model. And here we have the coefficients. The mean, the AR1 coefficient, alpha 0, and alpha 1. And all of them are statistically significant different from 0, right? That's my model. Okay. We call that model GARCH. I put the notes here. So we have, that's essentially what I told you about the tests. The one that we're going to pay more attention to is the jump box test. The Harke beta test, I put the explanation here, is testing the null hypothesis that residuals follow a normal distribution based on the bias and kurtosis. Okay. So the residuals may not have a normal distribution. These are the residuals for the complete model that has the AR1 model plus the Arch1 model. Okay. Shafiro weight test, just the residuals have the normal distribution also. And the other tests are used for their residuals and their squares. And they're based on the Young box. That's the one we're going to be paying attention to. Okay. So that's essentially the process to fit an ARMA model for the series, for the returns, and an arch model for the residuals. If I look at the structure of the model, I would call it model dot arch. Let's look at the structure of the model. And it does have all the information. It has the which function was called, formula, the method, the fit, and we have the residuals here down here someplace. Let me see where they are. I saw it. I saw them earlier. Let me see. I cannot go down here. My mouse got crazy. Okay. Okay, here they are, the residuals. Okay. So I may do here, I may do an ACF2 of model.large GNP, and then an ampersand residuals. Okay. And here I check only that the residuals do not have correlation. So in that sense, they seem to be, the model seems to be right. I could do a normal plot of the residuals also, but, and I could do a time series of the residuals. I would just have to do a plot of model.garch, GMP, arroba, residuals. And what I would expect to see here is roughly constant variance. okay? And there's a few outliers here, but that's fine. And I don't even do the normal probability plot because it doesn't gonna look normal, but you can do it. You have the script to do that type of plot, okay? So this is one example. If you want, if you can, no, try to go over the next example, which is the Dow Jones Industrial Average. Go over that example on your own, and tomorrow we'll do a couple of exercises to model so that you can model gauge effects. Okay, I'll stop